So let's now try to apply this new fundamental definition of what a voltage actually means to our first case. And we should always begin with the simplest possible case. So I want to implement this definition of voltage and see what we can learn about voltages coming from a very simple situation where all I have is a single point charge. So that will be our first application. So we're going to apply this then to the point charge. Now, for us to carry out this application, we're going to have a point charge here, which I will call Q. And we're going to need a diagram, as we'll see, to carry out the analysis. And as we carry out that analysis, I'll give you some tips on how to draw your diagram so that everything we want to be evident is quite clear in our particular diagram. So in this case, I've started out my charge down here in my lower corner of my page, not all the way down low, but pretty low. And then what I want to do is I want to draw a radius outward from point Q at some angle. A little bit of an angle actually will help, maybe like a 10-degree angle or something, so we can see that it's angular, like so. And then there's going to be a point out here, which will be a point X that will be involved in our integral. And as we're doing this integral, there's going to be a displacement from point X. And it helps when you make this displacement if we can continue this radius outward. So actually, let's label this R here. That represents my radius. And I'll put a little dashed line to make sure I'm continuing out along the same direction. And then I'm going to have a displacement vector that starts at X, and it will help if we choose that to be at some angle, maybe about a 45-degree angle from the dashed line, and extending for a reasonable distance, maybe something like so. And that will be a displacement vector. For now, I will just label the length of that displacement vector, and I'll just call that length a delta x right along the side of it. Finally, we're going to need the radius that goes from our charge as an origin all the way out to this new point. So we're going to draw a straight line from here to here and then continuing outward again with some dashed lines to indicate its continuation. It helps if you kind of practice back and forth a little bit with the tip of your pen before you actually try to draw that line and try to make it come straight out to go right through the head of that arrow. Yes! Looks like I made it. I forgot to turn it into a dashed line, but I think that's going to actually come out for us quite nicely. Now the next thing we're going to want to do then is to imagine that this is a little displacement along some path that for which I'm trying to calculate the voltage due to this particular point charge. So there's going to be some point A. I'll try to make the point A down here somewhere, a little further out and below my point X. I'll draw it here with an open circle. That will be the starting point of my path for which I'm computing the voltage. I want that path maybe to be some curved path. It has to kind of loop around and include this displacement though. And then after that it'll curve around maybe a little more, end up at some other point here that's further away from my initial point. I'll call this here point B. And now I can try to sketch out some kind of path from A that includes this segment up to B. So maybe I'll have a path that looks like this and continues outward and leaves A, goes along this delta x, comes out the top of the delta x, and then eventually works its way into point B. So that's the idea. I'm trying to calculate then the voltage along the path. Remember, voltage is a two-point function, to B from A, and this is going to be the voltage from a point charge, so I'll give it a superscript PT, our first example. And we know now from the definition of voltage that we'd given before that it's basically a work integral, so it's going to equal, there's this special minus sign as we have discussed, that comes about from the fact that we're calculating the work due to us, not the work done by this charge. There's work due to us, so there was that extra minus sign. And then we integrate all the force times distances, right? We've chopped our path up into a bunch of tiny displacements. So that will take us then, we're integrating from point A to point B. That's the pathway we're following of basically the force on the particle. But now, because we've divided out by charge, right? Voltage is to work what electric field is to force. So when we do voltages, when we want work, we integrate force, but we want voltage, which is work per charge, so we integrate force per charge. So we integrate the electric field along with its value at each of these points that we are traversing in our pathway, dotted with their displacements dx. Okay, so this is the diagram of what we're doing. This is the equation we're evaluating. Let's now carry out this integral. To carry out the integral, we're going to use the basic definitions of dot products and displacements. I'm going to write it down very formally here the first time we do it. When you guys do it, please feel free simply to treat, dx just like a regular variable. I'm going to just to avoid that here just the first time we try to carry out an integral like this. So this is then going to equal, and we know that an integral, of course, is just a Riemann sum. So this is minus, it's going to be a sum over a whole bunch of tiny little displacements along our pathway here of the electric field at each particular location x, then dotted with each displacement, delta x. And our next stage then is to, once we add up these sums, we'll take the limit as we have an infinite number of pieces, and the delta x's will eventually become dx's, right? But for now, let's just focus on dealing with this dot product. So to deal with the dot product, we always go very carefully step by step. The dot product is just the magnitude of each vector, the magnitude of E at point x, times the magnitude of the displacement delta x, times the cosine of the angle between those two vectors. So now we can begin to refer to our diagram to evaluate these quantities. The first quantity, the electric field at point x, this guy here is point x. The electric field there, we know, since there's only a single point charge, depends only on that point charge and this distance r, this radius, if you will. So we can indicate that as Coulomb's constant times the charge creating the field, which is q, that's the source of the field, divided by the distance r squared. So that's the electric field vector that this point feels. That's the magnitude of the field. The magnitude of delta x is, of course, as I've indicated to you here, that would be, if I'm at x, my little displacement is going to go from this point to this point. And the magnitude of that displacement is this delta x distance. So I will call that delta x. And then the angle theta is the angle between these two vectors. The electric field vector, we know, would just be pointing straight outwards, like so, if we had a positive charge, for instance. And the displacement vector is this vector going upwards in this direction. That's the delta x vector. So the angle we're referring to is actually just this angle in here, theta. So now we can begin to think about the geometry a little bit. If I have delta x and multiply by cosine theta, what I'm doing is I'm taking this thing here as a hypotenuse, and what I would want is the adjacent side to theta. I would want this side here, if I take this hypotenuse as a hypotenuse of a right triangle. So I need to drop a perpendicular then up from this bottom line to my point up here, so that's going to be a perpendicular, looks something like this. What I want you to notice, though, is that that perpendicular, here I'll draw my right angle, looks, right, that perpendicular is perpendicular to this longer radius here. If I remember, I'm trying to take the limit where this thing is very tiny, And I could imagine just taking a compass here and starting to sketch out the arc of a circle that goes through this point. The arc of that circle will look just like this perpendicular I'm trying to draw. So let me kind of sketch the arc of that circle here, like so. Make it look a little bit archy. And what I want to point out is that that corresponds very nicely to my triangle, but the radius of this circle is a little longer. It's r plus a little extra distance, which I will call delta r. As long as I'm thinking about these circles, this circle here is r plus delta r. That's the arc of this circle. There is, of course, a parallel arc at radius r. So let me sketch that in there, right? It also cuts in perpendicularly here. So it would kind of be sketching down like so. Good. The point of this discussion is that this delta x times cosine theta gives me this adjacent angle. This is my delta. This delta x times cosine theta I could also call delta r. Delta x there times cosine theta is delta r. Where r, and this is the point of our discussion now, notice, r is the distance to the initial point, x. This delta r, that would be the radius of this outer circle, but this outer circle tells you the radius r plus delta r, that's the distance to the point where I finally end up. So now I have a nice, I can reduce my sum to a very nice form. It looks like all that's relevant now is that I've got a summation, right? Taking all the quantities that I have here of Coulomb's constant times my charge divided by the distance squared to whatever point that I'm interested in, right? R squared. And then I just multiply that by the change in R for whatever interval I'm taking, delta R. What's really neat about this is it doesn't matter how I get from the inner distance r to the outer distance. I could take any delta x along these lines here, right, that I'm sketching here. I would always get the same result for this particular contribution. All that is relevant is this distance r from wherever I am towards the center. Now that we understand this, of course, we can now turn this back into an integral, right? If I take the limit of a large number of little infinitesimal changes and sum them up, what I'm doing is I have minus, I'm summing now over all these little changes, Coulomb's constant q over r squared times dr. And all that is relevant now, right, is my distance from my central charge. And so then what I'm integrating from is the initial distance, which would be at A, right, to the final distance, which would be, if you will, RB. So this is from RA to RB. And this now, I think, is an integral that we certainly can carry out. So let's now slide down a little bit and carry out our integral. So we're learning now that the voltage for a point charge as we go to B from point A is this integral that I've just indicated to you here, right? Minus the integral from the distance of point A to the distance of point B, distance measured to my point charge, Coulomb's constant q over r squared dr. And this is an integral we know how to do, right? If I'm integrating minus 1 over r squared, right? Or let's put it this way. If I integrate r squared, I can guess, right? The integral has to go like something like 1 over r. So inside here, let me put the guess for my integral. I'm surely going to have my constants, Coulomb's constant times q, divided by r. This would be a good first guess as to the indefinite integral. We always check by taking our derivative. If I take the derivative of this, I'll get back my constants, Coulomb's constant times q, which is exactly what I want. When I take the derivative of 1 over r, you'll recall that's r to the minus 1 power. So when I take the derivative, I get the power. I get minus 1, so I'll get a minus sign. And then the power goes down by 1. So I'll get minus 1 over r squared, which is almost exactly what I want, except I'm off by 1 minus sign. So I have to include the minus sign in here. And now this is definitely the indefinite integral that goes with that function, and the whole thing has to be evaluated between RB and RA. And at this point, you see, I notice I've got my two minus signs, which will nicely cancel. So I'll just put plus, plus, canceling them out. And our job then is simply to insert the two radii in for R. While I'm doing that, I'm going to factor out this common factor of Coulomb's constant times Q. So I have Coulomb's constant times Q. And then the difference is where I stick first the upper limit in. So that would be 1 over RB is what's left over in there. And then you subtract off what comes in from your lower limit, which would give me 1 over RA. The really neat thing you see here, notice, is that it doesn't matter at all, like we had hoped, if we have a conservative field, right? If we have a conservative force, it shouldn't matter what path I take from A to B. And the answer, notice, that we got out from here only depends on my initial distance, RA, and my final distance, RB. It does not at all depend on whatever crazy path I might take to get me from A to B. So it is actually totally path independent for our first example of the calculation of a voltage. Very good. So we'll talk to you next time, and we'll investigate more deeply some more complex situations, how we can handle more difficult cases. And you'll see very quickly that the principle of superposition will come to our rescue. Okay, we'll see you next time.